how the student's struggling to complete it is that the advisor has to step in and do a lot of work. Whereas our fallback is the student drops down to doing a course-only version without a project, or there's a thesis and then there's a project within the course-only version. And so it kind of puts the onus on the student, and that makes it a little bit less commitment for the faculty. So I, so that's just one more thing I'd like to kind of figure out.
Sure. Well, I mean, if you do want to, you can figure it out. Like, I would go about that. Because
sure.
For me, I definitely think I want to do for going forward in my career. I want to be able to say I have this project.
Yeah.
So for me, it's on me that it becomes
sure.
I'm not trying to push it off onto the teacher.
Right. No. I don't mean.
I just think you would have cooler. I think you would have more interesting topics. That's all.
Right. Yeah. So why don't you stop after class or in my office hours someday and chat more.
Sounds good. Thanks.
Professor, do you have time after class for some questions?
Yeah. I don't. I've got an hour or so after class sometime. So let's get started. So not sure what's going on with that projector today. So I guess that's why we have two. So I assume this is fine. Otherwise, I can spend a couple minutes troubleshooting. But okay. So great. So good. So it's here. So let's see. So we're starting a new topic today on regression. And so we've talked a lot about general sort of ways of dealing with lots of different sorts of data and lots of different distances or similarities between data and how you have all this modeling control. For the next several weeks, we're going to be kind of sticking to your data are vectors, and you're using something like the L2 distance. Okay, so it'll be a little bit more clean and focused. We're going to still use some of these ideas from the different sorts of norms and L2 distances and other ideas, but it's going to be kind of a cleaner kind of mathematical formulation as the basis of what's going on. And ask me questions if you want to know how something else relates, but we'll kind of see that as we go. So today is the 25th. That means that the frequent items homework is due on Wednesday. Hopefully this one is not too time consuming. A couple of parts we have to think about, the error bounds, but shouldn't be too difficult. After that, I think you don't have another homework assignment due for like a month. So that's good. And then what's big coming up is the midterm test is going to be a week from Wednesday. So let me just say a couple things about this now, and for you can start preparing for it and think of what kind of questions you're going to ask me about it. You can do that in later lectures too. But it's going to cover topics probably up through everything, including last week, but not starting today. Okay, starting today will be the main focus of stuff in the final exam, the end-term test. So this test might ask stuff before the midterm as well, but it'll mainly focus on stuff coming coming starting today. All right, so The goal is that we'll get hopefully something graded by the frequent items homework back before the test, so you can at least see if you were totally off on that or not. And so kind of the format will be, it'll be in this room, right? So everyone needs to be here. Okay, so if you're watching at home, don't forget to come in that day. It's happened. People come in late, like, oh shoot. So it means you'll be able to finish it in class, right? So it's not going to be, it can't be that long. In the past, I used to have this completely open book, but I don't like anyone to have out laptops or phones or even calculators, right? Just this modern technology nowadays, you can send notes back and forth, and there's no way I can keep track of it. But I decide I don't want people printing out the entire set of notes as well. What the deal will be is you'll get one piece of paper, like 8.5 by 11, kind of standard paper. You can use front and back. You can put anything you want on there. I don't care how you do it. You can work together to build stuff to share in class, but each of you gets one piece of paper. Okay. If you somehow get a copy of the test, don't put that on there. But you can have scrap paper as well. Okay, but come in with one sheet of paper. This is actually a good way to study, is to make a sheet of everything you would think you would need on there. There's some definitions that hopefully you'll know. They shouldn't be hard. They should be kind of inherent in just understanding what's going on. That you'll need. I'll try and make stuff fairly self-contained within the actual test itself. Okay, it'll probably be, you'll probably have like 3 pages with 3 questions on them, and each question will have lots of small parts to it, right? So we can kind of, it's not like, okay, you missed 1/3 of all the points and you lose all those, so we can give like lots of little pieces, but basically I'll cover probably 3 main topics that we've done throughout the semester, which will not be everything, right? But it'll be drawn from the first half of the class. All right, so does this seem reasonable? Okay. So if you have questions or complaints, please, you can let me know. It may or may not influence me, but feel free to give me kind of suggestions.
Will we post any midterms from last semester?
No, I don't plan to post any. I don't plan to post any midterms. So, the questions should be easier than the homework. Should be things I can ask, and some people will might finish in 15, 20 minutes. I would not be surprised. Some people will take until the end of the period, and it'll be everywhere in between. All right, so most people, if it's taking you towards the end, sometimes you're just very careful. Sometimes you're trying to recount stuff. But if you really know everything and you're really fast, you can finish it very quickly. Right? It should not be something that forces you to take a lot of time to do.
Will it be mostly proofs, theoretical understanding of the concepts, or are you going to give us the exact data sets to operate on and do some charting, for example?
Yeah, so I like to do stuff where I can actually give you the data sets. But as you can imagine, if the data sets are too big, then it's not feasible to do in the course of tests, right? So, but then I can ask you kind of mathematical questions about them as well. Right, so it's not just looking at data. It's going to be, I'll try and make it a mix, kind of like what we do in the class, what we discuss in the class, what you do in the homework. Hopefully it'll be a good coverage. But it should be something that, I used to call these just a quiz. You could think of it kind of like, you should kind of just know this if you're following along in the class. But it helps to study, especially if if you're not following along. These are important for your learning, actually, to have. I used to not have tests in this class, and students don't study as hard if you don't give them tests. And if you study harder, then you learn more. And my objective is for all of you to learn a lot. So that's why I have tests, not because I'm like vindictive or something like that. I'm trying to help you all learn. So, yeah.
What percentage of our grade is the test work?
Each one is 5% of your grade.
So the midterm and final?
No, the midterm is 5%, the final is 5%. The homeworks are 45%, the project is 45%. Yeah, so it's not a huge amount of your grade. Although there is more deviation in the scores on these than elsewhere. So but it's, yeah, so, okay. So good, so you have 2 more lectures and a week and a half to ask me more questions about it. But I haven't made it yet, so I don't know what's on it other than what I told you. So okay, and then closer we'll talk about the intermediate report. Actually, I will schedule meetings with all of you, all of the groups, individual meetings at some point around when the intermediate report is due, so we can actually force kind of 2 or 3 on 1 discussions, because I think this is kind of essential for doing a good project. All right, but we'll talk more about that later. Okay, so we're talking about regression. So, you know, I think of, so when most people think of regression, they think of, so linear regression, which is the most common form, and they usually think of what's called least squares, linear regression. And so I said we're doing kind of basically the Euclidean L2 sort of space, and we're basically going to be focused on variance of least squares regression. But kind of regression is, you know, I like to think of it as a much more general thing. There are a couple ways to generalize it. I'll just mention these before we kind of go into a tour. Today's lecture is basically a tour of least squares regression and the main variance, and then we'll dive deeper into a few parts. But I like to think of, there's a couple ways to think of it. One is that, so there's the so there's like the supervised learning, and there's there's unsupervised learning, and you could think of these as being classification, and so regression also fits in here, and the difference, and then clustering would be in this cell, and so that these two, that the outcome is going to be a set, right? So I'm getting a data point, and in a cluster I say it's in one of the 3 clusters I found. It's in one of these sets. With the difference between supervised and unsupervised learning is that with classification, I'm given labels ahead of time. I say these, I'm predicting this person is going to pass the class, this person is going to fail the class. And so I have details of past students, and I mean, most people pass this class, but so don't worry too much about it. But but you know, I can look at how well they're doing up to this point in the class and make a prediction: are they going to pass or fail? I know what the labels are, and that's the supervised part. I'm giving labels. So this is, with clustering, I'm not given labels. I'm just given data. I'm told to group the students into groups, and maybe that corresponds with pass-fail, but I'm not told it has to do that. So regression is supervised in that we're given labels, but it's not, the outcome is not a set. Now the outcome is going to be a scalar. So it's going to be a value. I'm predicting a value. So if I'm predicting the value of your grade, right, I'm predicting you're going to get 93.7% when I average out everything over the breakdown of the grade we just discussed. That's going to be regression instead of classification, right? And then the other square here is dimensionality reduction, which we'll talk about just after a break. Right, so this is an imperfect kind of model of everything in data mining and machine learning. the only supervised learning we're doing in this class is the stuff on regression here. So we're going to be given scalar values, and we're given data, and our task is to predict more scalar values. Okay, so this is kind of fairly broad way of viewing it. Another way of thinking about regression, another broad way of thinking about it is that you're given some data, and again, I like to think of data as points, and you're somehow trying to fit some sort of model, and the model can either be a line or it can be a set of points, like in clustering, and then I want to use this model to give me some scalar value. So I'll draw this as a vector representing the length of the scalar associated with each point in the model. And then you can think of the regression as mapping everything onto the closest data point. So with the assignment-based clustering, I'm mapping everything onto the data point, and then that has a representative value. So I could take the average of all the scalar values in a cluster and predict each data point has that average scalar value. That would be something like a regression. I'm regressing onto the center of the cluster. But in linear regression, which is a typical way, you have some linear model, and you're mapping all the data points onto here, and then you can have some scalar value defined on the line, and then you use that scalar value. All right, so I'm somehow mapping onto a model, right? Some model M. It could be a cluster, it could be a line, it could be lots of other things. It could be kind of a shape, right? I could regress onto, you look at brain scans, you look at what's an average brain look like, and you have a model of a brain, and you regress onto the average brain, and that helps you predict which region is which, right? So there are lots of ways you can think of this regression. Okay, so it's a fairly general thing. There are these nonlinear approaches that use kind of kernels that works as regression, and it's similar in that it can fit a function on this general line. Okay, so there's this kind of broad topic, but we're going to look specifically at like this things based on linear least squares versions of regression. Okay, and so it starts with two data sets. So the data input, okay, now is going to be x and some y. And so this y in this case is going to be a scalar, it's actually a scalar vector. Okay, so that's kind of confusing notation. So, I mean, that's opposed to the classification setting where it's just a binary label. So these are both, in the simple setting, we'll talk about where this is going to be the explanatory variable, and this will be the dependent variable. Okay, so we're going to look at the data in X and use it to try and guess what the data is in Y. Okay, and so you could think of this as Y. This is going to be Y is, so both of these, so this one is going to be an Rn. So if I'm going to have n data points, so the way one data point is going to be an xi, yi, which is going to be in the set from xy, right? So one data point is going to have, and if I have n of these data points, it's going to have a scalar value. So this entry here, this will be yi, and this is going to be a scalar. And I want to try and predict some model which is going to take in this vector, this maybe a matrix, but in general, this x. Okay, and so I kind of want to, I want to start out where the case where this is also in Rn. So it's just also going to be a vector. We're going to start with this case, but in general, it's going to be an n cross d. So each xi, right, that corresponds with the yi here, right? So if this is xi, then this is going to be an element of Rd. It's going to be a d-dimensional point, right? So before, when I drew, you think of clustering these d-dimensional points, you know, or as d-dimensional vectors. Now I'm thinking of, I want to predict a scalar value with these d-dimensional vectors. And I want to learn some model which takes this data and for every data point predicts a corresponding y. Okay? And if this is going to be a linear model, then m of xi is going to be some alpha, we'll call this m alpha, is just going to be a dot product with xi. Okay, so if it's a linear model, a linear regression is just going to be just a dot product here. And so alpha is then going to be alpha 1, alpha 2, up to alpha d. Okay, and sometimes you also carry some offset parameter. You can have a constant here, which is part of your model, or you can fold that into here. Okay, so we'll come back to this. Okay, but let's start now. Okay, let's keep narrowing down to the simplest case. Now I'm going to say that x is in Rn and y is in Rn, which means that I'm going to have one-dimensional points for x and one-dimensional values for y. And the nice thing about this is I can now finally draw a picture. And luckily, x becomes on the x-axis and y becomes on the y-axis, right? So this is might be close to how you'd like to think about it. And then for all the input here, I'm going to think of some data points like this, right? So if this is some data point, this is xi, yi. This is one data point. This value here is xi, and this value here is yi, right? So it's a two-dimensional coordinate here, all right? And like in general, right? So if this space down here can be Rd, right? So then I have these extra dimensions down here, and I can have a d-dimensional point, but it's predicting a y scalar value. Okay, but now let's just draw everything just in this simple two-dimensional case, because there's a lot interesting that happens here. Okay, and it's easier to see what's going on. Okay, and now the linear model, remember our model m alpha of xi is now going to be a dot product, but it's just going to be alpha 1, comma, xi, right? So this dot product, but these are both, because these are scalars, right? Then it's just multiplication of alpha 1 and xi, or just alpha and xi, right? So I just have alpha times xi plus b, some offset. And what does that look like in the picture here? So this alpha is going to be this kind of the slope of this line, and b is this offset. Okay, so this is what the model looks like. Hopefully, most of you have seen this sort of picture before of what linear regression is. I'm trying to fit a one-dimensional line through this data set. It corresponds in general with the dot product, but right now a coefficient times x. This is the amount. Every time I move x a little bit, I increase the value by alpha. It can be negative and decrease. And b is the offset. How much, if x is 0, then how much is the baseline of the model? Okay? Right? And then what's important to see in this picture, I think probably that hopefully you've also seen, but if not, just to be clear, is that the error is now measured entirely in this y direction here. Okay, so the error of this data set xi, this is the residual. this is equal to yi minus the model alpha of xi. So this is what I'd say is the error of this one data point, is this y distance. It is not this error, right? So you think maps it to the closest point on the line, and maybe that's my error. That's not what it is. This is not error. It's only in the y direction. Okay, and this is kind of important. I care about predicting this y value, so my error is only how much error I get in this one y direction here. Okay, and so if I have more dimensions down here, I'm still only predicting error in this one y direction. Okay, good. And then so the least squares formulation is to, now my goal is to find alpha and b to minimize the sum I equals 1 to n of these Ri values squared. So that's least squares. This is the square. I'm looking at these residuals. I square them. Turns out because it makes the math easier in various ways, and it's easier to solve. And I sum up all these. Okay, so it's okay to have one really bad thing as long as on average the square distance is small. Okay, so this is the ordinary least squares so regression problem. Okay, just when the explanatory variables are just one dimensional. Okay, so has anyone not seen this before? Okay, good. So we can move on more quickly. Okay, so one thing to know is that there's a closed form solution for this. Okay, and so basically, let me just write this down. So actually, let me first write the extensions of this. So let's say, so there's, it turns out to extend this to higher dimensions instead, now when x is in Rn times d and y is in Rn, right? So now I have d-dimensional explanatory variables. The goal is to, I've got some y here, and I've got some data set x here, where now probably I don't want that many coordinates. This is x, and my goal is to find a vector alpha, right? Alpha now is d-dimensional, right? So this is d-dimensional, this is n-dimensional, and this is d-dimensional. Goal is to find an alpha where I approximately recover this y, right? So I want to find alpha to minimize what's now y minus x alpha squared. So this two-norm vector, right? So for every data point x, I'm right. This is actually yeah. So I'm getting a vector that approximates x times alpha gives me a vector which approximates y, and I look at the L2 norm between these, and I can look at the squared version, or I can take a square root. It has the minimum value is the same. All right, so I want to find the alpha which minimizes this, and so one thing, this setting does not have the offset in it, but I can add a column here that's all ones here, and then I have an extra variable alpha, say d plus 1, and now the model is going to be x 1 times alpha So now the model F alpha of xi is going to be the dot product of xi comma 1 times alpha, and now alpha equals alpha 1, alpha 2, up to alpha d plus 1, where the alpha d plus 1 here is now the offset. So I don't need to worry about the offset anymore. I can encode it into this matrix X. Okay, so now we can just think about not having this offset case, which is essentially just is now a technical condition. We don't need to worry about it. And now I can solve a closed form for solving for alpha. There's this magical linear algebra I can do. So now pretend X is actually the matrix with the 1s column added, and alpha is equal to X transpose X, the inverse of this, X transpose times Y. Okay, so there's a closed form solution for the alpha which minimizes this squared objective function. Okay, it involves, I take this matrix X, and I take the transpose times itself, I take the inverse, and I multiply by the transpose again, and by Y, and this magically gives me the right solution for alpha. This is alpha star is minimized by this expression. Okay, so there's this magical way I solve it if I set up this formulation. Largely, this is because of this and other computational niceties, this is why the least squared version is often studied. It's very easy to solve. It gives you the exact right solution.
So if you're able to inverse the product of transpose and X, it's guaranteed that all the vectors are linearly independent in that matrix, basically. And it's a square matrix that you get.
Right, so this becomes a D by D matrix, if I did this correct. So usually you have more rows than you have columns, and you need to say that it's full rank. Right, so that each of the columns are going to be linearly independent. That's right. We'll see. One things we'll talk about here is how to deal with the case when that's not true. We'll talk about this. Right. Okay, so there's this closed form solution. Kind of in practice on really large data sets, you actually set up typically, you actually don't want to do this inverse. This is kind of expensive, so you'd set up a gradient descent formulation actually instead. And it turns out you can do stochastic gradient descent, and it works pretty well in this sort of setting. But we'll think about just the closed form solution for now. That'll be sufficient. So there's also the polynomial extension. Okay, so that means that instead of fitting, so let's look at now this simple case again, where X is just one-dimensional, and I have data that looks instead kind of like this, okay? And I don't want to fit a linear line through this anymore. I'd rather fit, say, an order 3 polynomial through this data. I think this is a better model for what's going on. It turns out this is not really any more difficult to solve than the linear case, right? And so now what my model is going to be is the error in this case is still going to be measuring just the error in the y direction, okay? And that's what makes this work. Now my model alpha is going to look like for some value x, for some xi, is going to be alpha 0 plus alpha 1 xi plus alpha 2 xi squared plus alpha 3 xi cubed, right? So any polynomial curve up to degree 3 will look something like this. This is the form of any polynomial curve, okay? And so to solve this, I just convert this into a matrix representation where I turn it into some x x3, where I'm going to put the first column is going to be all 1s. This is x1, x2, x3, up to xn is the next column. The third column is x1 squared, x2 squared, x3 squared, up to xn squared. And this is x1 cubed, x2 cubed, x3 cubed, xn cubed. Right, so I've created a new matrix. And then to solve for this, well, this is actually a dot product between alpha and 1 xi squared, xi cubed. Right, so the model is still a dot product here. And it's a dot product with a row of this matrix. So now to solve for alpha star 3 in this setting, I just have to take this matrix, x3 transpose, x3 inverse, x3 transpose y. Right, so and this is a closed form for the polynomial version. Okay, so I want to fit a polynomial curve. I just do this expansion into this matrix. And then I solve it the same way, and it's still it still minimizes the sum of these squared vertical errors. Okay, so I can again solve this polynomial thing basically just as easy as the linear thing. Okay, if I have multiple dimensions down here, I need to look at all possible, say, order 2 or order 3 combinations of these. So I need to do a much bigger expansion, and maybe the first coordinate squared, the first coordinate times the second coordinate, the third coordinate squared, plus the linear terms plus the constant terms, right? So the expansion becomes bigger, but you can do the same things, right? So I can do a polynomial model on top of kind of data. Basically, there's still a closed form. The gradient descent approach still works as before. Okay, so I get these nicer and more complex polynomial models as well. If I want a different sort of model, I think there's some coefficient times a cosine. I can make one of these rows a cosine of xi and pre-fill it in here, and then I can solve for that. Right? So as long as I'm solving for just coefficients of some predefined sort of expansion, I can solve for that very easily in a closed form. Okay, so has everyone seen this before? Or? Yep. So, okay, good. I think in the previous class, this was about 2 or 3 lectures, right? So trying to go fast without going too fast. All right. So, okay, so in fact, there's this thing called the Gauss-Markov Theorem. Okay, so who's heard of the Gauss-Markov Theorem? Have we covered this before? Just a few of you? Okay, good. So this is saying that if my goal, so if the goal, and we'll just talk about the two-dimensional case now, but it extends to all these other cases. If the goal is an alpha to minimize y minus x alpha, where y and x are going to be y and x are going to be vectors, right? For y, x, and Rn, right? This extends to the high-dimensional version. Let me just write this down. If the goal is to minimize this, right, and I want expected error, or I want the expected residual Ri, which is yi minus xi alpha, to be equal to 0. Okay, so I want the expected residual to be 0, and I want to, and I assume that Ri is uncorrelated with Rj for I not equal to j. Right? So I assume that 2 data points are basically the errors between them. There's no known correlation between them. Right? If I assume correlation, everything becomes much trickier, and we won't even do that in this class. So I assume that the residual errors are uncorrelated with each other. Okay, then the alpha starred equals to x transpose x inverse x transpose y is optimal, and it's optimal in the sense that it minimizes this. It minimizes the sum of the squared errors, which means that the variance, so the variance on the set Ri is as small as possible. Okay, so it basically says if my goal is to minimize the variance, the amount of error by the sum of squared errors, and this is as good as I can possibly do. If I make these assumptions that the expected residual is 0, which seems reasonable, and there's no correlation between any of the errors. Okay, so this is almost saying, okay, this is probably pretty close to as far as you may have learned stuff like this before, and saying, okay, this is optimal, we can stop here. Okay? It turns out that this is not necessarily the right place to stop. Okay, we have another 2.5 lectures on this topic, so we aren't going to stop here. Okay? So in what way do you think that this theorem is like anytime you read a statement like this, you should say, okay, this is great. Does this solve everything, or are there sums, do I have to assume too much here? Right? There's something I'm assuming here, which it turns out is it's best not to assume. No, so it turns out, so this is, okay, so you can do more stuff if you assume this. This is hard to change. It's hard to deal with the correlation residuals. There are definitely whole subfields that deal with this. They're not in the scope of this class. Yeah.
Is it that you have normally distributed errors?
So partially, right? So so there's this thing that I'm minimizing the variance, which means I'm minimizing the sum of the squared things, which essentially implies that the error is that I'm given the x-coordinate, I'm given the model, and then there's a normal distribution which is causing the error in this residual, right? And so that's essentially the underlying assumption, and that's something we can change, but that's not where most of the field has moved beyond this. But there are ways to do that. So that would be like putting, for instance, if I wanted Laplace error instead, if you know what that is, then I would minimize the sum of the residuals instead of the sum of the squared residuals. Turns out this is much harder to do to solve for the solution. We're going to do something as nearly as similar of a solution. Right? So I am actually going to still assume that the errors are normally distributed.
Is it because we can't always get 0 error?
What? Right, well, we can't always, so we could do something with a polynomial model where we actually get 0 error, but we actually don't want to, you're kind of pretty close in that we aren't going to restrict that the expected, expected residual, we're not going to restrict that the expected residual is 0. Okay, it's not that we can't get it, we can find the one that has, this solution has expected residual 0. For if I drew in a model I described, if these are drawn IID, but we're not going to restrict that the expected residual has to be 0. And this will actually allow us to do better. We're going to get a smaller variance solution by adding some bias. Okay, we're going to bias our solution in a way. It's going to mean that the expected residual is going to be greater than 0, or it's going to be different from 0, but the overall sum of squared errors is actually going to decrease. Okay? Right, and so it turns out this will also help us deal with outliers in a way that's better. Actually, trying to model this as the sum of the residuals instead of those, absolute value of the residuals also does better with error, but that's going to be harder to calculate. So we're going to deal with something that a simple change, which will allow us to kind of deal with outliers much better, and is going to reduce the variance of our estimator overall. And there's a version of this which is actually going to enforce that in high dimensions, when you have lots of coordinates, that there's sparsity, that some of these coordinates are going to be forced to be 0, which means I don't want my prediction to be based on something which has a small effect. Right, so I want to make my prediction as simple as possible, and it turns out this is related to this idea of regressing to add a bias, which is actually going to also reduce the overall variance of the estimator. Okay, so we're going to add a bias, so the expected Ri is not going to be equal to 0, but this is going to reduce the variance on the set of residuals, and it's going to, in some case, it's going to induce sparsity, which implies that some alpha j will equal to 0. So I'll essentially implicitly force some of the alpha j's to be 0. Sometimes explicitly, depends on how we solve it. All right, okay. So this idea is called, there are a few names for it. I'll describe 2 of them. Tikhonov so Tikhonov regularization. This is also called ridge regression. Okay? And so this is going to be a simple way of adding a bias. I'm going to have a new error model. I'm going to call this L2S. And there's going to be, the 2 is for the L2, the sum of the squares. The S is going to be a parameter. We have X, and I'll have some alpha. And now to measure the error, or let's say I'll have X, Y, and alpha. Okay, it's going to be the sum xi and x of yi minus alpha. Right, so this part is the same, and the important thing is I'm going to add an extra term here. So I'm adding a bias term to my cost function. The original part, this part is the same as, this is the least squares. This is the same as before, right? So I have this dot product model with xi. I want to solve for alpha, right? I want to solve for alpha to minimize this. That's sum of the squared residuals, right? And now I'm adding some bias term here. So this is saying I have some parameter s, which is part of my error function. I'll have to somehow decide what s is. But say I'm given s, right? You could think of it as 1 if you're confused, right? And then I want to make alpha small. If the alpha, my model parameters are small, this is better. So I want to bias to having a smaller model parameters. Okay. So if I draw a picture, okay, and for simplicity, let's just say that the data, that the model can go through the origin, the least squares model. So now just don't worry, assume the offset is built into the xi, right? This is y. So this is the least squares solution. And now this is the ridge solution. And we'll have a smaller alpha value, which means as x gets larger, further away from the origin, it's not going to rise as much. We're going to tend to have smaller slopes. It's kind of the effect of this model. Okay? Maybe this isn't, and maybe this is the wrong parameter. Maybe there's a different parameter which kind of sits through the middle here. Right? So depending on how I change s, the larger I make s, the smaller the slopes have to be. Because I want to minimize this expression, the more weight I put on making the slope small. If I make s super, super large, I'm just going to get a model with all zeros. Not very interesting. Right? But some s in somewhere, and if I make s 0, I get back the original least squares. S in between is going to be, one of these I claim is going to be better than the original least squares. And maybe this is it. Maybe there were some outliers up here, right, which are pulling the least squares model up. Right? So these are pulling the least squares model up, and maybe most of the data is in the middle here. So this actually does, this prediction ends up actually being better, perhaps. Okay, so if I chose S better, then maybe this actually is a lower variance solution. Okay, and so the proof that you can get around this Gauss-Markov theorem is basically you can set up, you can look at you can look at the derivative of this, and right, with respect to alpha, and you can see that as the alpha values decrease, the bias term is going to decrease, and the least squares term is actually going to increase. But for certain values of s, if you make s small enough, then what's going to happen is the bias term will, or if you set it right, will decrease faster than the least squares increase, which proves that there must be something better. So this is actually, it's non-constructive. So I don't know what the right value of s is, but there's some value of s which is better. And we'll see in another lecture like a good way of how to choose s. Okay. One of the other nice things about this is there's still a closed form solution. So I have this nice thing where I have alpha star was equal to x transpose x inverse x transpose y, right? I could solve for alpha star exactly. And it turns out that if I add an s parameter here, right? So this is the s parameter. Then I just do an s squared identity. So I put a d by d identity matrix, and I put an s squared terms in front. I put this inside of the inverse. And this is the right closed form solution for this formulation. So I can add a bias term, which is going to give me kind of models which are going to have lower slopes, and I still get the exact solution for this. Okay, so, and it still plugs into kind of gradient descent the same way as before. It's just as simple, right? Because I have, this is also an L2 kind of bias on the coordinates. Okay, so I still have a closed form solution. It's just as easy to solve as before if I know the value of s. All right, so this is kind of a common extension to least squares. All right, so aside from some claim that this is going to give me smaller variance for some value of s, why would I want to have why would I want to have this solution instead? Right? Other than like I could pretend that this is the right picture, I can create a data set and show you as well, but other than saying this kind of intuitively, what's other intuition why I would want to have this value of parameter model instead of the one where s is 0? Yeah?
Yeah, potential to reduce like overfitting. So like making our models fit too closely to the data, the sample.
Yes. So one of the dangers of these squares, especially if you have very high dimensional data or you fit a very high polynomial, is you can try and fit the data too much, and you try and essentially try and hit every data point. But when you see new data, which is ultimately what the goal is going to be, you aren't going to do as well. You're not going to predict as well when you see new data you haven't seen before, where you only get the x value and you want to predict the y value. Right? So in this cross-validation view of it, we'll talk more about cross-validation. I switched the order of some lectures around, so this will come later in the semester unless I move things. You can hope that this is not going to overfit. Okay, so I'm going to do better when I see new data. Okay, so good. So this is the right way to think about it, but why would I think this would do better why would I think this model would not overfit when the ordinary least squares one would? Let's kind of intuitively, like, what could possibly be better?
Well, because you're inducing the sparsity, so you're like forcing some parameters to be 0, right?
Yeah, so this model, this ridge regression is not going to induce sparsity, it turns out. Okay, we'll talk about the next model, like kind of lasso, which will do this. So there's other reasons why you think a sparser model could be better. But ridge regression is already going to do better for the right value of s, is going to do better under cross-validation without inducing any sparsity. It's just going to make the coefficients smaller. Right? What's an intuition? What's good about making the coefficients smaller? What would really large coefficients look like? Yeah, so let's draw a picture. Okay, and this is x, this is y, and let's say that the data happen to look kind of like this. Okay, so now what's happening here is that the least squares model might fit something like this, least squares model. So so the intercept might be down here, where a ridge regression model might fit something like this. Maybe that's too much. Might do instead, this is for S. This is for S large. Right? So larger the S, the smaller it kind of forces these parameters to be. If the data, so the least squares model is kind of going through the core of the data. Why would you want, I would argue you want the ridge regression model here.
Because if you have the new data coming in, for example, you have much bigger probability that it's going to be concentrated. You have the ridge regression model coming in. So
the hope is that, right? that if you have new data coming in, and I just get the x value, the ridge regression will do a better job of predicting what's going on. Right? So I want to think about, kind of one way of thinking about that is instead of having new data come in, let's take one of these data points, which has error here or here, right? And let's say there was a little bit of noise in the x-coordinate, right? The x-coordinate. So if it shifts a small amount over to here, the least squares model is going to change more than the ridge regression model. It turns out the ridge regression model got even closer here, but this was just lucky. It could have been someplace else. But so as I get error in the x-coordinate, it means smaller change in the y-coordinate. So it's less sensitive to changes in the explanatory part. If I have center error, then I'm collecting my data. I change it a little bit. It's going to be less sensitive to that, right? So I'd rather have a flatter model that kind of is not sensitive to small changes in the x-coordinate, in the explanatory variables, right? And so this is my kind of intuitive reason why I like to think this is better. You can write down the math and see that too, but I just think it's more stable in terms of the stuff. Whereas these other models, they're basically assuming, it's built into the models, you assume when you get an x-coordinate, you know it exactly. And that's probably not true, right? Maybe it's true, but it's usually an estimate. So it's more stable in here, and I think this helps a lot.
So how do you choose the optimal S value?
So how do you choose the optimal S value? Okay, so let me give you, so let me just say, now we'll have a big part of a lecture, on this later. Choose S by cross validation. Okay, so who's not heard of cross validation before? So I think, okay, so most of you have heard. If you haven't heard about this, so the basic idea is we'll talk about this and some general ideas around it later on in the semester. But the idea is you take your data and you split it into a test set and a training set, and you train the model based on the training data model. I get all the x's. So I go back to this picture. I randomly choose a bunch of columns here as the train, and I solve for the optimal alpha on these, and then the remaining columns are the test. Okay, these are the and then I choose the value of S that does best in prediction on the testing. So I randomly split them into two parts, and I train on the training parts, and then I use some leftover data to kind of evaluate, to figure out which S parameter gives me the best prediction. Okay, and so this is the cross-validation framework, and it's very powerful in supervised learning. Okay, so in unsupervised learning, you can't really use this, but in supervised learning, like clustering, I don't know how to use an idea like this, but for supervised learning, this is the right way to select model parameters, including like this S. Is there a question?
Is there a correct way to split? Because it was a 50-50 split?
It depends on how much data you have. I'll just talk more about this, but usually you want to say take 10% of your data or 30%. The more data you have, the less test data you need. And the more trained data you have, the better model you can actually build, and you need enough test data to know that you can trust the solution. So the values of S that you're getting. Those are usually easier because they're just one parameter, whereas the model might be more complex. So you'd rather have more data there. Okay. Okay, so the ridge regression does not induce sparsity. To induce sparsity, I need to change this just a little bit, and this will be a technique called lasso. It also has other names. So basis pursuit is often associated with this. This might actually be the name of an algorithm. These are kind of common terms associated with this other version of the model. And this will be the version that induces sparsity. Okay, and so I'm going to call this L1S. Okay, and I'm going to change the objective function a little bit again. So I'm going to start with, again, I'm going to, let's get out of hand. All right, so for every data point, I'm going to look at the right. So I'm going to have the least squares part of it, and I'm going to add again residual here. But now I'm going to add a regularization term. But now this is going to be an L1 regularization term. So instead of the L2, which I used before for the ridge regression, which had this nice closed form solution, everything is L2, everything is nice, I'm making an L1 regularization. And so that means that the sum of the absolute value of the coordinates, right, is what I'm penalizing. Instead of just the standard L2 norm, I'm using the L1 norm here. And so this is what's called the Lasso formulation. And so this change induces sparsity. Now, this does not have kind of this clean closed form solution. We'll see we'll see most of the next two lectures will actually be ways of solving for this and interpreting why this induces sparsity. There is actually an algorithm which is an exact algorithm to solve for the alpha which minimizes this. Turns out it's more complicated, and you can kind of do gradient descent, but this objective is going to be convex, but because it has absolute values, it's not going to have a continuous first derivative. Okay, so if you're familiar with all these gradient descent techniques, because it does not have a continuous first derivative, this will cause some issues with the doing the gradient descent. Turns out you can usually kind of deal with these. It's pretty simple, right? You just have the absolute value, so the derivative is only non-zero at certain points, and you can kind of generally work around these. But it's a little bit harder to optimize. Okay, so that's why initially this wasn't used, but then not terribly kind of long ago, it was realized that this formulation induces sparsity by changing this regularization term to be an L1 instead of an L2. Yeah?
You might cover this in future lectures, but what's meant by sparsity in this context?
Sparsity means so sum alpha j are equal to exactly 0. So I want, think of the case where the number of model parameters is very large, say 100, and I want 5 or 10 of them to be non-zero. That would be sparse. And so we'll see algorithms that will find these optimal or almost optimal model parameters in this case. Yeah. Okay, so I want to. So we're going to talk more about this. Yeah. Okay. So let me say there are two other. Let me do a preview of two other forms of this. So both lasso and ridge regression, you can write them. This is kind of a soft optimization criteria. You can do like a hard optimization criteria, and let me call that L1T, which is going to be x, y, alpha, the same as before. And here, just kind of some more intuition of what's going on. So this part is the same. I still have the least squares terms, but now I can say I have a t parameter instead of an s parameter, and I want to say such that the L1 norm of s is less than or equal to t. Okay? And I can do the same thing with the ridge regression instead. And we'll actually look at pictures and interpret what this means. But I want to say now that this is an equivalent, effectively equivalent formulation. Okay, so it means that for every solution I find with this version, with the L1, the T version, where I have the hard constraint, that I enforce all the model parameters. I say I want to minimize least squares. That's my objective. Okay, but I'm going to force the model parameters must be within this L1 ball, or if the ridge version is in an L2 ball, right, I can enforce that the same. I say for every solution of this type, there's an equivalence. There's another, for every S parameter, there exists a T parameter that gives me the same solution. Right? So for all alpha S star, there exists a T such that alpha S star equals alpha T star. Okay, so I can find an optimal alpha of a T star which matches this. Okay, and so how would I do that? I can I can solve it under this constraint. Don't worry about how I solve it yet. And then I'm going to I'll solve it under the L1S constraint, under the soft constraint. Okay, and then I look at whatever the L1 norm of the alpha parameter is, and I set that value to T, right? And that's going to be the right solution for this for the hard constraint formulation, right? So if I solve alpha S star equals arg min alpha of L1 S x y alpha, then I set T equals the L1 norm of, right? If I set T this, then I argue that if I, this is the right, then alpha S star equals alpha T star, which is the argument of this formulation. So because if there was another solution that had the same norm, it would have to have a larger least squares formulation, because this was the one that minimized the least squares formulation. It minimized it with this L1 constraint, right? And so if I so of all the ones with this norm, that's the best solution. And if I, I mean, there's some cases, and then you have to just reason about if you actually shrink the norm, can it possibly be even better? But it's usually better to have a larger norm. That's not always the case if you include the best solution, but in general, that'll be the case here. Right, so these formulations are equivalent, and it turns out this one will be, the hard constraint one will be easier to reason about. Usually the optimization one is what people use because they can plug it into gradient descent, but this one is going to be nicer to think about, and that's what we'll discuss in a version that we'll discuss in the next lecture. Okay. And I can make the same argument with ridge regression as well. So I just want to, while I'm talking about least squares in general, I just want to mention two other ways around so Gauss-Markov. All right, so there are two other formulations which are in some ways better than least squares, which are different than adding this regularization term, that are somehow better, even though Gauss-Markov theorem says that the least squares is the best way to think about this. So the first one is these robust estimators. Okay, and so this is the idea that my data is generated by some, so my data x, y is IID from some sort of model, and how this model works is that there's some, so there's some probability of noise, and there's some probability of data, and this one basically looks like yi equals alpha x plus some epsilon, and this may be like normally distributed, right? So assume some fraction of my data is generated, and this may be equals, say, 0.95. So 95% of the data is generated IID from this model where it's some dot product plus some Gaussian noise or something else. And with this one, it's just going to be, large and weird, right? Okay, so, so think of most of the data kind of looks like we would expect. It kind of looks like there's some line that generated, and then there's some Gaussian noise, and that the rest of it is like all over the place, right? And some of these could be extreme outliers. Okay? And all I really know is that, let's say, this is a small constant fraction of all the data. Okay, so I have these extreme outliers, which makes up some fraction of my model, but the rest of them is pretty well behaved. Okay? In this case, they could be all extreme in the same direction, right? So doing the regularization terms, ridge regression and lasso will help in this regard, but there are other ways of dealing with this too. The same way that if I have a one-dimensional distribution and I want to find an estimator, the mean is one way to estimate as a single data point, and the median would be another. But if I add one data point all the way out here, outlier, what's going to happen is the mean is going to shift, and the median will basically stay in the same spot. One outlier could pull the mean arbitrarily far towards outlier, okay? Where the median will basically stay in the same spot. Okay? It's robust in that a small constant fraction of the data is not going to pull the estimator out of the region where the 95% of the data is. Okay, now least squares regression, and basically any form of it, is going to have the same sort of issue. It's based on least squares, and the mean is a least squares estimate. So can we make it more like the median? One way to do this is kind of thinking like setting up an L1 cost function instead of a least squares. But there are these other ways that basically try to use something like the median instead. And so what they'll do is they'll take, there are these things called the Theo San Estimator. I think is the most common form of this. And what this does is it takes So it takes all pairs. It looks at all pairs of these data points. Okay, so it looks at all pairs of the data points. It estimates the slope of all of these slopes. So I get all of these different slopes. Right, so I have basically n choose 2 slopes, and I take the median instead. Okay, so I look at all these pairs. Each pair gives me a slope, and I sort them left to right in this way, and then I take the median of these slopes, and this will actually give me a robust estimator, I think, as long as like less than 29% of the data are outliers. Okay, 30% of the data are outliers, this could still have something arbitrarily bad. But if it's less than 29% of the data are outliers, then this one will give me something inside of the shape of the 95% of the data. Okay, so there are these entirely other approaches meant to deal with outliers that kind of are trying to do something like a median, but for these more complex models. And there's a whole line of literature meant for doing these things, which we are not going to explore in the rest of the semester, but I just want to mention them here. All right, so we'll talk more, next time about we'll get more into this lasso approach, how to compute it, why does it do sparsity, and we'll talk about this problem called compressed sensing, where you can actually recover some models exactly, assuming that there's sparsity. If you assume there's sparsity, you can actually recover the exact model, even if there's noise.